Hello, my name is Álvaro González, and today I would like to present to you our work related to an optimal scenario reduction method for a stochastic power system problem. This work was done together with Professor David Pozo from Skoltech in Russia. So, as we know, renewable energy generation installation is increasing year after year, and most of the installation of renewable energy is related to wind and solar energy projects. However, this introduction of wind and solar in our system introduces stochasticity or randomness in the operation of the power systems, because these sources of energy depend on climatological factors that cannot be controlled and most of the time are not 100% predictable. So how do we actually make decisions taking into account this uncertainty for our system operation? A really popular approach in power system literatures is the use of two-stage stochastic programming. And in this approach, we have two stages. In the first one, we have a scheduling decision. So we decide how our machines are going to operate, our power plants. Are they going to be turned on or off? And then in the second stage, we have the operative decision. That means that it's a decision that is going to depend on the first stage. If the machine was on, then we can actually generate power and adjust it in the real time. And these different decisions that are taken on the operative stage depend on discrete scenarios that can be generated for each one of the possible outcomes of renewable generation that we have in our system. And this can be based either on forecasting information or historical data. And how do we increase the accuracy of our representation of uncertainty? In this case, we should just employ more information or more scenarios to have a more accurate decision or closer to the optimal. However, when we do this, we increase the number of scenarios, we also increase the complexity of our problem and its computational time for resolution. What we did in this work was to apply the generalized adaptative partition-based method to power system problems. This methodology was created by Ramirez, Pico, and Moreno, who proved that we can actually reduce the number of scenarios that we use in an optimal manner by dividing them into partitions. And how do we choose these partitions? We basically need to satisfy the condition that the optimal partitions are generated when the dual multipliers of the scenarios in those partitions have the same value. So in the case of power systems, we can think as the dual multipliers as those related, for instance, with the electricity price, and those are the dual multipliers related to the energy balance constraint. And we can use those as our indicator. Since this is a combinatorial problem where we need to assign scenarios to partitions, the authors developed an iterative method in which we can actually assign properly the scenarios to the partition while obtaining an optimality gap. So how do we actually apply this? We tested this on a wind sizing problem. And as we can see here in the first iteration of this method, we can see that the scenarios are divided in two, depending on the dual values. Then we have in the third iteration 4 partitions, and then in the final iteration we have 5 partitions that are going to give us the optimal value of our variables of interest. If we compare this with methods that are popular in the power system literature, such as k-means and methods related to Kantarovich distance, we see that each one of these methods, they give us a different separation or organization of the scenarios, while also giving a large gap greater than 5%. We also tested this investment problem with 10,000 of scenarios, and we can see that the different variations of the generalized adaptative partition method give lower gaps, while also giving lower resolution times. For instance, for the sample average approximation, we can see that the solution times is really high. And for those methods based on Kantarovich distance, we see that they have a large overhead, while also not guaranteeing a good optimality gap. So thank you for your attention. And if you have any questions, please don't hesitate to contact us.